एक डेस्कटॉप ऑडियो, हाँ, और उसकी बंद कर दी थी ना। चेंज मत करियो, रहने दे, डेस्कटॉप ऑडियो ऑन रहने दे।
Data dominates. If you have chosen the data structure and organized things well, the algorithm will almost always be self-evident. Data structures, not algorithms, are central to programming. On this note, I welcome you all on behalf of Creator Garage and Computer Club on the day 3 of DSA Bootcamp. I hope you all enjoyed 2 days of the bootcamp. So let's start another amazing day with amazing people. It's a pleasure for me to introduce our speaker for today, Mr. Murtaza Ali. He is a data engineer at Kites.ai, a senior coordinator at Computer Club SDSITS. He is a CP enthusiast and a leader at CodeShift SDSITS chapter. Today, he will be sharing his knowledge on trees with us. So, without any delay, let's invite our speaker. Over to you, sir.
Guys, how's it been? So it's Murtaza here, a final year student from Computer Club, and let's dive right into the session. So yeah, so over the course of the past 2 days, you have been like studying data structures. You have studied 4 data structures till now. That's arrays, linked lists, stacks, and queues. So could any one of you like quickly, I would like to keep this session really interactive. So please be responsive in the chat box. So let me ask you a question quickly. Like, what is common between all those 4 data structures? Like, come on, just quickly write anything that comes to your mind. Anything common between all those 4 data structures, that is array, linked list, stacks, and queues. User defined, okay, they are all user defined, but yeah, kind of. Anything else? Come on guys, be interactive. So like don't make this boring for me. Yeah, so science is linear. So yeah, that's correct. All of those 4 data structures were linear. Okay, group of similar data. Yeah, so we are actually studying only homogeneous data structures. Yeah, so I'm getting those responses now. So yeah, that's correct. It's data stored in sequence. Correct. So data was stored in linear sequence in all of those data structures. That was the one thing common. So till now we have been studying. Basically, it's organized, but it's not. The data is not stored in linear fashion. So let's quickly jump into it. So what is a tree? So tree data structure is basically invert that one tree. Like this is a tree, we just invert it. And yeah, a tree data structure is basically an inverted tree. So you might ask like, Murtaza, like, are you kidding me? Like what's similar between these two? Like there exists almost no, like if you see there exists some similarity. So let's see what is similar here. So what can we see here? That there is one starting node here. So we can see that, like, take this node for example, or this point somewhere here. This can be taken as the starting point. Then take some linkages here. Like there are some links to like other nodes. So you can see the branches coming out of this. So you can say that these are linkages. Now, in a tree, there are branches coming out of more, like one branch, there's a one branch, and there are multiple branches coming out of that. So there are more branches here. Similarly, you can see there are more branches here. So in this way, you can kind of relate with a real world tree. You can also see that in trees, there is leaf. So a leaf doesn't have any branches coming out of it, right? So kind of similar. These nodes are called leaves. We will get into it, but yeah, there are no branches coming out of it. You can see there are no links and like nothing is coming out of it. It only has a parent. So that's about like an introduction to like basically what is a tree. Now, before we get into it, like could you like let's like tell me a word which could really like describe what is a tree. Like you might have studied in third or fourth class, or even like when you were like describing the structure of a family, or maybe something like what do we say, uh, like classification, for example, classification. Like maybe you were doing classification in your class 9th and 10th. Yeah, I'm already getting correct answers. So yeah, correct, hierarchy. So what a tree represents is basically hierarchy. So it's not an official name, but yeah, you can basically say that a tree is a hierarchy. So this is a hierarchy here. I'm really weak in bio, so don't expect me to understand this. But I guess you guys get it, right? So this here represents a hierarchy. So basically, this is what a tree is. A tree has a root node, and then there are multiple nodes coming out of it. So a tree is a hierarchical data structure defined as a collection of nodes. All of these are called nodes. You must have learned on the first day of your session when Nivesh told you about linked list. So linked list has nodes. A node is like something called, you can say, a primitive, like something primitive data structure which is used to like store values. So these nodes are basically how these nodes are connected, what defines the data structure. So here we have a root node, and then there are multiple nodes connected from it, and then in turn there are more nodes connected to it. You can see like animal is connected to mammal and reptiles, and then reptiles there's snake, there's bird and lizard, and multiple categories. So hierarchical data structure defined as a collection of nodes, and nodes are connected by edges. So these thing here, this linkages, what I was saying as links or linkages, in a formal definition of data structures, it's called as edges. So these are the edges here, and you will always use these terms to like represent the links or linkages even in trees, graphs, or any other data structure. So that's it. A tree, the properties of a tree. Okay. So a tree has only one node called root. Like you could see in this tree, there is a root, and from that root, like a tree grows from that bottom, from a seed. That first part of the tree is a root. So that's where the analogy was basically derived. So a tree has one node called root, and it is the origin. Rest of the nodes originate from that one root, and hence it does not have any parent. Like it is the origin, so origin doesn't have a parent. So as you can see, reptile has a parent animal, mammal has a parent animal, snake has a parent reptile, but animal does not have a parent. So root does not have a parent. Now each node has one parent only, but can have multiple children. Now this is one of the fundamental properties of a tree, that each node can only have one and only one parent. So you can see here, reptile has only one parent. Like you can basically see the structure. Every node only has one parent. Only root node has no parent, and each node is connected to its children via the edge. So there are edges all over the nodes. So I guess you get it. So like let's continue. I'll check if there are any doubts here. Okay. Okay, so I don't see any doubts. So let's continue with this. So cool. Basic terminologies of a tree. So we have learned about parent, we have learned about root, we have learned about edge. Now, what are children? So children are basically the most the most recent descendants of a node. Like those who immediately descend the node are its children. For example, E, F, G are children of L. L is children of A. But this E, F, G are also related to A, but they are grandchildren of A. Okay, it's kind of like your family tree only. Like in a tree, your mother and father are above you. You are derived from them. So you are the children. So kind of similar analogy in a tree. You have a parent. A parent can have multiple children, but children only have one parent here. And then there's siblings. So I guess you know who siblings are. How are you and your siblings related? Like, could you write in the chat box, I guess? How are you and your siblings related? Okay, could you please explain edge once again? Okay, let's just get over this children. So how are you and your siblings related? Parent, exactly. So as you can see here, a node, these all the siblings have only one parent. So yeah, that's about it. That this node here, sorry. So this Q node here has A and B as its children. These two are siblings because it has a common parent. So nodes which have a common parent are siblings. And like this is not official terminology, but yeah, you can even define like cousins in a tree. Like there are questions, they are not official terminology. Like there is nothing called as cousin, but yeah, you get it. Like you can basically define those. So what are cousins? Basically their parents must have the same parent, like your family tree again. So A and B are cousins of C and D. C and D and siblings, A and B are siblings, but A and B and C are D, how are they related? They are cousins. So yeah, you can like basically form similar terminologies. Then there's edge. Okay, so what are edges? Edges are basically linkages in any data structure. Like you must have seen linked list. So they are called linked list because the nodes are linked to one another, right? So how are they linked? Because of an edge. So edge is kind of like think it of as an imaginary connection between two nodes basically. Like it's basically used to define a relationship. Like how are you related to your parents? You are children of your parents. So that children is kind of a relationship. Like it defines you. Like Like there is no hardcore evidence. It's just a relationship. So think of it as a relationship. An edge is a relationship, and then there's nodes, and nodes are related to each other by relationships. So if this P is your parent, then R is you, and this relationship is basically P is parent of, like you can define this relationship as parent of R. So P is parent of R. So kind of like understand edge as a relationship. So edge is you get it. It's a connection between nodes. So okay, I will check if there's any doubts. Cool. So okay, then there's subtree, like subtree. So what is a subtree? So like there is a node A, like take P for example, right? So a tree is defined by its root. Okay, the P is the root node, and it has an entire tree below it. So subtree, as you can see, it's a subset of a tree. Subtree is basically short for subset of a tree. So what are subsets? They are part of a set. Like this, sorry. For example, this this here is a bigger set. So this part is a subset of this bigger set. So similarly, this entire structure here is the subset of this bigger structure, which of which P is the root. Like P is the root of this bigger tree, and Q is the root of this smaller tree, which is a subtree of P, of the original tree. So L is also a subtree of this big tree. So basically, what subtree is, it's a subset of that tree. Understand it like that. So like anything, you can take this tree as a subtree. So here A will be the root. Here in this subtree, you guys like, could you write in the chat box? Like keep interacting with me. It will be better. Like what will be the root of this smaller subtree? Anyone? Okay, L. Cool. Yeah. So it's a basic question. So yeah, L is the root of this subtree. So basically, where the tree originates from, the node from where the tree originates from, it's the root node, and the rest of the part is the tree. So subtree is the subset of that tree. Then comes the leaf nodes. So you know leaf nodes, we discuss it in the tree. Those nodes which does not have any children, or in a real world example, leaves don't have branches coming out of it. So there are no branches coming out of it. There are in this terminology, there are no edges coming out of it. Like there are edges going inside this. Okay, like don't get me wrong. There are edges going inside here like this, but there are none coming out of this. So when edges are not coming out of it, then this part is called a leaf node. So in a real tree, there are no branches coming out. Here, there are no edges coming out. Think it of as a node with no children is a leaf node. You can see these nodes does not have any children. These nodes does not have any children. This node does not have any children. So all of these nodes, this node also does not have any children. So all of these nodes are called leaf nodes. So I hope you are with me at this point. Right? Guys, please respond. Like, are you with me on this point till here or not? Yep. Cool. Excellent. So let's continue with the rest. So okay. So now we move on to levels. Like forget this key for now. It's kind of gray area for now, because we might cover it in future, but it's not the plan right now. What is this key exactly? So let's come on another thing called levels. So what are levels? So in a tree, like for example, that hierarchy we seen just now. So animal was on the like the topmost level, right? And then there were multiple levels. Like on level 0, it was animal, the topmost level. Then on level 1, we have a general specialization. Sorry, yeah. The more we move downwards in the tree, the more we have specialization. Like animal is more of a vague term. Like we are now properly dividing it into two categories called reptile and mammal. So we have specialized categories from that animal. So we are on level 1. Now we further specialize that category into reptiles, into lizard, snake, and bird. So we are basically moving down the levels, or like increasing those specializations. Like we are getting like more and more closer to that exact thing. Like if we want to get close to a salamander, then salamander is an animal is more of a vague thing. Like we can say salamander is an animal. Yeah, salamander is a reptile. Yeah, that makes things much more clear. Salamander is a lizard. It makes it much more clear. So that's what I'm getting at. Basically, levels are a level at which those nodes are present. So this root node is always present at level 0. Then its children are present at level 1. Its grandchildren are present at level 2. Its great grandchildren are present at level 3, and so on. You can basically see it here. A is the root node. It's present at level 0. Its children at level 1, and so on. So these are basically levels of a tree, and these levels itself are also called depth of a tree. So like you guys, we will get to it. We will get to depth and height of a tree. But for now, I guess this much is clear for all of you guys. Yeah. So okay. So if you want to like yeah, so these are the basic terms. These are basically all the same terms which I have explained, so I won't like spend much time on this slide. You can read the basic definitions of what is a root, a parent, a child, a leaf, an edge. Then we have siblings. Then we have path. Okay, we have not covered path yet, I guess. So path is basically a path. All right. So what do you mean by path? A path is basically connection between two nodes, or like a way where we can reach from one node to another, right? So a path from, suppose, a node P to a node B will be called P, then Q, then B. So this is the path from P to B, two nodes. So a path between two nodes is basically the nodes which are like we are going from one node to another node. So all the nodes which we encounter in between are present in that path. A path is basically a connection between those two nodes. So if we are to define a path between, suppose, A and M, so I guess you could like define it simply as A, then there is a edge here, then Q, then an edge here, then P, edge R, then edge C, and then edge M. So this here is the I know my writing is very bad, but please bear with me. Yeah, so this path here is a path between node A to node M, right? So could anyone of you tell me what is the length of this path? You have the path in front of you, A, Q, P, R, C, M. Could you please tell me, like anyone in the chat box, what should be the length of this path? Five, right? See, any other answers? Oh, accidentally removed it, but yeah. I get 5 and 6 and 4. All right. Majority is currently with 5, I guess. Yeah. So I will be moving on. So yeah, the answer to this question is 5. Why? Because A, sorry. So we have A, then a link, then Q, P, then R, C, and M. So we do not calculate the number of nodes in a path. We always calculate the number of edges. So please bear this in mind. Then we always calculate the number of edges. So how many edges are there? We have an edge from A to Q, 1, Q to P, 2, 3, 4, and 5. So because we have 5 edges, the length of this path will be 5. So please bear this in mind, that length of the path will always be the number of edges between those two nodes. If we are calculating the path between Q and P, these two nodes, then the length of the path will be 1 and not 2. We are not counting the number of nodes, we are always counting the number of edges. Please remember that. Yeah. And do we have any doubt? I actually saw one doubt. Utpal, do we count root node while counting the height? Yeah, so we will get on the height thing. I have kept it as a separate topic because it's a little bit complicated. Levels we have covered, height of, we will get on the height thing. Then there's degree of the node, subtree, internal nodes, ancestor and descendant. So ancestor and descendant I will cover first. Ancestor is simply, you have seen your family tree. So who are your ancestors? Basically those above you. So those nodes which are present in the path between you and the root node. For example, let's take L, right? So taking L here, this node L, we have this path PQAL. So this and in this entire path, P, Q, and A, all of them are ancestors of L. All right, like you start from the root node and you go to whatever node that you wish to analyze your ancestors on. So if you wish to know the ancestors of L, all those nodes which are coming on the path from the root node to that node will be its ancestors. So P, Q, and A will be the ancestors of L. Similarly, the descendants, you know your family tree again. So you are the descendants of your parent, you are the descendants of your grandparent, you are the descendants of your great grandparent, right? So this Q is a descendant of P, this R is the descendant of P. In fact, all the nodes which are derived from this root node are descendants of this root node P. So all of these nodes are descendants of P. And for example, who are the descendants of Q? So all of these nodes which are present here, like A, B, L, E, F, G, all of these nodes are descendants of Q. But hey, C and D are not descendants of Q. Remember that. Even though they are present at a lower level, they are not directly related to Q. Get it? Like root node is being separated into Q and R. So C and D will be the descendants of R, that is this node, but C and D won't be the descendants of A and B. Like for example, your uncle, Chacha, I am talking about. So you are not descendants of your uncle, you are descendant of your father. So that's what I'm talking about, that A and B will be descendants of Q, but they will not be descendants of R. So the node, which again, you form a path from the current node to the root node. So for F, you get L, A, Q, and P as your ancestors. So you are the descendant of your ancestors. You are not the descendants of any node other than your ancestors, right? So think it of that way. The path that you create from root node to the current node, all the nodes except yourself will be your ancestors, and you will be the descendant of all of your ancestors. Kind of like family tree. Think it in that way, like a family tree. Do I have? Okay, cool. So moving on to the next slide, I think we have covered it. And then there's internal nodes. Yeah, internal nodes are those nodes which are not leaf, and external nodes are leaf nodes. That's it, nothing more. Right? Internal nodes, like for example, this P, Q, A, B, all of these are internal nodes, and these E, F, G, which are basically the leaf nodes, they are external nodes, and that's it. Then there's degree of node. Okay, so you can see degree of node represents the number of children of a node. So the number of children a node has, it's simply the degree of the node. That's it. Then you know the subtree, descendants of a node represent a subtree. So descendant of this Q. Yeah. So let's kind of make it more cleaner. Yeah. So descendant of this node Q, it's A, B, L, E, F, G. This represent the subtree of the Q. Sorry, the tree of the Q, and this QAB thing entirely will be the subtree of T. So that's how I think. I think I've made all of it clear. Are there any doubts? Like, would you like me to like quickly go through a topic again? Please write it in the chat box. Cool. I guess there are no doubts. So let's proceed with it. Depth and height. So now we have come to one of our main topics, that is depth and height. So what is depth is the number of edges from the root to that node. So as I've said before, depth and level are basically one and the same thing. But the definitions may differ a little. Level are again, as I've explained, levels are like the level of hierarchy which is present in the tree. Like it's on level 0, it's on level 1, it's on level 2. And depth is the number of edges from the root to the node. Like you could also define the level as same as the depth. So depth or level, basically it is the number of edges from the root to the node. So you start from this here, this node A. So C, if you choose C, so you can see that the number of edge from root to C is 1. So depth is 1. And if you choose H, so you can see the number of edges from A to H, the path from A to H. So it is 1, 2, and 3. So hence the depth of the node is 3. That's it. So you get the depth. It's basically kind of same as the level, but yeah, like you can basically for now you can understand it as same as the level of a node. Now comes the height. So there are people who like get confused between depth and height. So depth is the number of edges from the root of the node. That is, we are taking the path from the top of the node. The height of a node is the number of edges from the node to the deepest leaf in the subtree, right? So we begin from the current node and we see what is the like the deepest possible node which is present in the subtree of that node. So you know subtree, like for example, if we take B, like so what will be the tree of B, or basically the subtree? This one. Sorry. This part here will be the subtree of B. So we need like we will need to find what is the deepest like which node is present at the deepest possible level. So we can see here that H is present at the bottommost level in this subtree, right? So the height of H will be 0 because there is no node present below it. The height of E is 1. Now you can see one thing. Height of F is 0, height of D is 0, but height of E is 1. So even though D, E, F, all three of them are present at the exact same level, still there is a difference in their heights. That's simply because we always check height in the subtree and not in the entire tree. Like we don't compare height by levels. We always compare height inside a subtree. So when we are checking for the height of E, we are checking it in E's subtree. So what will the E subtree? It will be this. So it will be just E and H. So you can see the deepest node is present at like the distance between the deepest node and E is 1. That is, there is one edge. So therefore the height is 1. But here you can see the subtree ends itself here, like it's a leaf node, it doesn't have a subtree. So the height of a leaf node is always 0. Remember that. The height of a leaf node is always 0. So here also the height will be 0. Now for B, we will be checking like what is the maximum possible height out of all of its children. Like we have height 0, height 1 and height 0. So we will take the maximum possible height and then add 1 to it, because there is one connection here, one connection here, one connection here. So if we would have taken D or F, we would have gotten the height 1. But we know that height is the maximum number of edges from the node to the deepest leaf in the subtree. The deepest leaf, we are talking about the deepest leaf, right, in the subtree. So here we will take the maximum value of all the heights, that is 1, and then add 1 to it, because there is a path from B to E, and that will be the height of B. Simple. So the height of B will be equal to 2. And similarly for A, the height from this subtree also the height is coming out to be 2, and from this subtree also the height is coming out to be 2. So we can basically get the height of A will be equal to 2, take either of them, 2 plus 1 equal to 3. So again, just for the sake of explanation, depth is taken from the top, that is from the, we compare it from the root node, but height we compare it from the deepest leaf in that subtree only. So I hope it's clear. If you have any doubts, please let me know. Okay. Okay, I will assume that you guys have no doubts and we will take them later. So yeah, binary trees. So till now we have seen like trees having multiple children and like there are multiple number of edges and stuff. But now we will strictly be talking about binary trees. So what are binary trees? A tree whose element have at most 2 children. That is, if there's this node, it will only have 2 children, and because it has only 2 children, we can basically define it as left child and right child, because it's only 2 children, right? So yeah, that's about it. And yeah, it contains a left reference and a right reference. Reference means these links. Basically these links are called references. And if you have studied C, you know them as pointers. If you have studied Java, you know them as references. This is the structure of a node in a binary tree. This is a node. A node has like you can store any type of data, not only integer data, that is in data. You can even store like anything like string, float, and anything. You can even store your custom data structure here. And then the references which I was talking about, these are the references. A reference to a node. That's what we are referencing to a reference here. So node, there is a left node and a right node, basically a left child and a right child. So as I explained, a binary tree can only have at most 2 children, that is the left and right child. And yeah, that's about the binary trees. So this here is also a binary tree. Basically it only has left child, and this is a type of binary tree. We will get into that later. But yeah, remember that a binary tree has only 2 children and it follows all the same properties as the tree that we have seen before. That is the siblings thing. It has one root. The root has no parent. Node can only have one parent. All the properties of a tree are followed here. The only thing here is it can have at most 2 children. properties of a binary tree. So these are general things, general, like for curious minds, basically these are mathematics kind of thing. I will quickly go through them, and you can see the proof in the links I've mentioned in the references. So maximum number of nodes at a level L of a binary tree is 2 to the power L. So let's take any level. For example, let's take level 1. So this is a binary tree. So what is the maximum number of nodes I can fill on level 1? This is level 0 currently, and then there's level 1 here. So I can fill, I guess, 2 nodes here. So can I fill more nodes? No, I can't fill. So maximum number of nodes is 2 to the power L. That will be 1 here, and that is 2. So there's 2 nodes here, and if we have to like calculate the maximum number of nodes on level 2, so how many nodes can we fill at max on any level? So there will be 2 nodes here and 2 nodes here. So in the end, we have, like, this is the level 2, and the number of nodes we can see it as 4. So 2 to the power level, that is 2, will be equal to 4. So you know this statement holds for any kind of binary tree. You can look for the proof in the references that I have mentioned at the end of the slide. So the maximum number of nodes in a binary tree of height h is 2 to the power h plus 1 minus 1. So let's look at the same tree. Maximum number of nodes in a binary tree. So this is a fully filled binary tree. You will see the types of binary tree, but for now, like, we can't add any more node in this binary tree without increasing its level. For example, like if I add a node here, we will increase its level to 3. So we don't want to do that. We basically let's just keep it at level 2. So this is the maximum number of nodes we can fill in this level. So what is the height of this binary tree? I guess that will be the maximum level. I think you guys get it already. So just okay, good. So yeah, what is the maximum height of this binary tree? So it will be 2. That will be the maximum number of levels in a binary tree. So height is 2. So you can see 2 to the power h plus 1 will be equal to 3. So 2 to the power 3 is 8. 2 to the power 2 plus 1, that is 3, which will be 8. And it's 2 to the power h plus 1 minus 1. So 8 minus 1, that is 7. So you can see here 1, 2, 3, 4, 5, 6, 7. There are 7 nodes. So this property holds for every binary tree. Again, you can check for the proof in the links I have provided in the references. In a binary tree with n nodes, minimum possible height or the minimum number of levels is log 2 n plus 1. So if a binary tree contains n nodes, for example, so what will be the minimum possible height? So what do you think should be the condition for the minimum possible height? So that should be basically if we like club those nodes as like closely as possible. That is, we fill as much levels as possible. Like for example, this here we are like having like this is called a skewed tree. We will see about it later. But yeah, it like it exceeds the like minimum possible height. Like we could like include this node here, and we could have included this node here. So like if we wanted a tree with 4 nodes, we could very well, like, this is more of a tightly packed. Yeah, the word I was searching for is tightly packed. So tightly pack a tree as much as you can. So you can find the minimum possible height of or the minimum number of levels. So that would be log 2 base n plus 1. So for 4 nodes, you can see log of that 4 nodes. There's 4 nodes, right? So sorry, yeah, there's 4 nodes. So it will be 4 plus 1, that is 5. So log base 2 and 5 will be something like, I guess, more than 2. I guess, yeah, it will be something more than 2 point something, right? So what is the maximum level here? You can see it's 2. So So that's how you can get it. And like it is the minimum, it is the minimum possible level, right? So if you are creating a skewed tree like this, so it goes till level 3, but we are only like asking for the minimum possible height. So yeah, that's true. This is the most tightly packed tree we can have. A binary tree with L leaves has at least log base 2 L plus 1 levels. So yeah, this is also like something like you could derive from actually this. You could derive it from this. Like you could see this as the maximum number of nodes at level L of a binary tree is 2 to the power L. So let's take it as 2 to the power L. All right. Now this is the maximum number of nodes at a level. So let's like assume that this is the bottommost level and this level is entirely filled. All right. So this 2 to the power L will be equal to like there are the maximum number of nodes. So for example, let's take 2 to the power L. This will be the maximum number of nodes, and 2 to the power h plus 1. The total number of nodes will be 2 to the power L plus 1 minus 1. So what we are basically doing is a tree with L leaves. So how many leaves does this tree with 2 to the power L plus 1 minus 1 has? It's 2 to the power L. This is the maximum amount of leaves it can have, right? And we are calculating the least number of levels, right? Okay, so I guess it had a proof. Okay, so 2 to the power L plus 1. Yeah, okay. So 2 to the power L plus 1 minus 1 is equal to the total maximum number of leaves. Like, yeah. So we can simply take log on both sides. So it will be L will be equal to log of L, and yeah, it should be actually plus 1 here. So sorry, minus 1 here, because the total number of nodes in a tree is 2 to the power L plus 1. Yeah. So let's take this L to be h something. So basically here it will be 2 to the power h minus 1. So here this we are basically having h minus 1 here, and we are sending this minus 1 to there. So it will be log base 2 L plus 1. You can look for this proof again on the Geek for Geeks website that I have mentioned. And again, in a binary tree where every node has 0 or 2 children, the number of leaf nodes is always 1 more than the number menstrual children. Okay, so we can kind of verify this property as like, let's see this. So this is one of the binary tree, right? And it should have 0 or 2 children. So let's make it also 2 children. So you can see the number of parents are 2 and the number of children are 3. So this property also holds for every binary tree with either 0 or 2 children. So again, you can verify this. Types of binary tree. Now we are on types of binary tree. So a full binary tree is called a full binary tree basically if every node has either 0 or 2 children. So that's what we were talking about here. It either has 0 or 2 children. This is a leaf node, and this node contains 2 children, and these children contain 0 children. So this is a full binary tree. A complete binary tree is basically all the nodes are like present at the leftmost as left as possible. Basically, we are filling the tree in this fashion. Like first we will fill the entire 0th level, then we will fill the entire first level, then we will fill the entire second level. For example, there is a node here, then we will first fill this node, then this node, then we will come to this node, this node. So every level is completely filled, only then we are moving to the next level. Like we are like this here is not a complete binary tree, because we have like not filled this level yet, but we have already moved to the next level. So this is not a complete binary tree. But if we do it like this, like first we fill this level and then move on to the next level, so this is a complete binary tree. So that's it. And then there's perfect binary tree. Basically it always contains 2 to the power h plus 1 minus 1 nodes. It's perfect, it's completely filled, it's the most tightly packed binary tree, like this here. And you can see the example itself. This like the leaf nodes contains 0 children, and all the internal nodes, you know what internal nodes are, right? External nodes are leaf nodes, internal nodes are all the nodes which are not leaf nodes. So all the other nodes contains 2 children, and all the leaf nodes are on the same level. So that's what a perfect binary tree is. You should just know the basic definitions. They are not really as important, but yeah, they are still important. Now we are on tree traversals, right? So first, just let me confirm. Okay. Are we following it till now? I hope that we are following it. I see no responses, so I guess we are following it. Yeah. So we are on tree traversals. So what are tree traversals? Like first thing you could ask me, like Murtaza, like what about insertion and deletion? We have learned that in arrays, we have learned that in linked lists, tags and queues. Why not we have learned it in trees yet? So simple answer, my most basic answer is they are not as important. Like you will encounter trees mainly, like I'm not saying always, but mainly in interviews, and primarily not in coding questions. They are kind of different kind of trees. They are like the special case of graph trees, and they will be covered tomorrow. But yeah, binary trees you will always encounter like only in interviews. So assume that you are always given a tree. For now, forget about insertion and deletion. You can read about them later. For now, we are assuming that we are always given a tree, and the operations which are performed in the tree are more important. So we'll be proceeding with that. So depth first search. So what is depth first search? As the name implies, we go in the depth first, and then we care about the rest of the things. Like for example, yeah. For example, let's make a tree here. So let's take more notes here. Okay, cool. This is a binary tree. So depth first search, how it proceeds is we go inside this depth first, and then we come out, and then we just go as deep as we can in this fashion until we can no longer go more deeper, and then we move to the top, and then again, like we always move from left to right? So we begin, we go as deep as left as possible. As you can see here, we are going as deep as left, then we can't go any deeper. So we will check for right if there are any right children, and if there, we will go towards right, else we will return. So we are returning here, then we go, we check, yeah, this node contains a right children. So we will go deeper inside, then we go in the left child first, then we can't go any deeper, we move back up, then we check, okay, this node also has a right child, so we can go deeper here. So we can go deeper, we see that they have no children, so we just move up and up till we reach the node from where we have started, and then we will move on to the right subtree. Basically it's always left subtree and then right subtree. So we move to the root node, then we again start moving in deeper, and you can basically see this pattern, right? Like in this way we have moved from this subtree in this fashion. Basically we are traversing it as deep as possible first, and then moving up and then going to the other subtree. First we move to the left, then we move to the right subtree. So that's how we basically do the depth first search and breadth first search. Now, breadth first search, you won't be able to relate it as much, but I think the other term you will be able to relate it much better. That is called a level order traversal. So what a level order traversal is, as it implies in the name, we travel level by level. So you have seen these levels here, right? So in the breadth first search, we travel level by level. So first we travel all the nodes on level 0, then we travel all the nodes on level 1, then we travel all nodes on level 2, and so on. So you can see that first we have traversed A, then B to C, and yeah, we always travel from left to right. Like in special cases, in questions which may require that you travel from right to left, the case is different. But yeah, in level order traversal, we always travel from left to right. So first we are covering level 0, then level 1, then level 2, and so on. So this is about the level order traversal. Now you can see there are three things, like three types in depth first search, right? There is pre-order, in-order, and post-order. So what are these? So as you remember, I've told you to always travel from left and right. So let's just write L and R here 3 times in front of pre-order, level order, in-order, and post-order. So we have, like, we are traveling from left subtree to right subtree. So pre. So what does this pre, in, and post mean? So what do these mean is exactly what we are referring basically to the current node. That is, if this is the binary tree that we are talking about. So if we are in this node, then this we are referencing as the current node. So like we might have to, like, we can do various things on binary tree. Like we can take sum of all nodes. We can simply print the value of the node. That's it. Or we can do other things. So what we call this term is process. So how we process the node is what these pre, in, and post order things mean. So like for example, simply printing the value of this node is also processing this node. So pre, in, and post are basically the order in which we process the current node. So pre means first, it comes before anything else. So we process the current node first, then the left subtree, then the right subtree. In order, it comes between, like in left and right. So we process it in between left subtree and right subtree. In post order, last. So we process the left subtree first, then the right subtree, and then the current node. So these are basically what is meant by pre-order, in-order, and post-order traversals. And you know, breadth first search. So moving ahead with depth first search. So the algorithm of pre-order, in-order, and post-order is entirely similar, except the time at which we process these nodes. So, you know, in pre-order, we first process the current node, and in order, we process the node between, like, first we call the left subtree, then we process the current node, and then we call the right subtree. And in post order, we first process the left, then the right, and then we process the current node. So this is the basic difference. In the recursive approach, basically, guys, do you know about recursion? Like, this is a really important thing to know. Like, could you like quickly tell me if you know about recursion? You guys must have studied recursion. Okay. Okay, I will give a brief introduction on recursion, like a really quick one, because we are kind of running out of time. Yeah, function calling itself would be a basic definition. Yeah, correct. Yeah, function would call itself. Cool. Yeah. So basically, what recursion is, like most of you guys are correct. The function calling itself but it's like going within the depth of the current function. For example, the tree is also called a recursive data structure simply because recursion is the best way to like process a tree. For example, we are on this node, then we move to this and this node. So we are going in depth, like the depth of the tree. So if we are on the, suppose the name of the function is pre-order, right? So if we call the function pre-order on root, so we are currently on this node, all right? So pre-order, let's call it on root. Then in this step, that is visit the root, we simply print the value of the root, and then we call the pre-order function on the left subtree. How do we call it? That's basically pre-order, the function name, and we pass the left subtree in it. How do we pass the left subtree? We simply pass the left node. So it will be root dot left. So that's simply how we like the function is calling itself. Like we are in the pre-order function, and the pre-order is calling itself, but the value is changed. Like first it was called on this node, then it is called on this node, then it is called on this node, then it's called on this node. Like you can see, like it's first called on this node, then this called its left subtree, it's called on this node. It calls then it because it does not have any children, it moves back to its parent. Then this parent calls the right subtree. It's defined here. It will be simply be root dot right. Then it does not have any children, so it move upwards. It has traversed both of its children, so it move upwards. Then this root node call its right subtree. You can actually see this in the code here. You might need to like practice recursion a bit to understand this tree data structure, although you can understand it easily even now. But yeah, recursion would be a good way to understand it. So this is the Java code. But yeah, like for example, in pre-order, we were posting the value of key first, then we are calling the function on the left node, yeah, and then we are calling the function on the right node or the right child. In order, we are doing this printing thing in between, and in post order, you guys can see we are doing this in the end. So that's it. That's the basic difference. Now, you guys have studied stacks and queues, right? Ivan like taught you to yesterday. So I would like to invite Ivan to take over to like explain you how this stack thing works with depth first search, and how we can like how you can exactly visualize this pre, in order, and post order traversal. Ivan, to you.
Yes, sir. So, um, is my screen visible to all of you?
Yeah, Ivan, it's now.
Yeah. So, let's start with the example of pre-order traversal with the help of stacks. So, since sir have explained you how to have a traversal with the help of recursion, let's study how to have a recursion, how to have a traversal with the help of stacks. So, in the stacks, what we have to do, let's suppose we have 7 elements, right, from 1 to 7, and the representation of these 7 elements is something like this. So what we have to do now, we have to traverse these elements in the pre-order, right? In the pre-order we have to traverse these elements. So what we have to first we have to go to this element, right, to the first element, and the process will be something like this. So we have the current node, right? We have the left subtree and we have the right subtree. So first, what we have to do in the pre-order traversal, first we will print the current node, then we will print all the nodes that are present in the left subtree, and then we will print all the nodes that are present in the right subtree. So what will be the representation here? First we will be printing 1, which is our current node, right? then what we have to print? We have to print the left subtree. In the left subtree, we have the first element as 2. So we will print 2 here. Then what we need to do? We have to print the left subtree of 2 as well. So in the left subtree of 2, we have 4. Then since here we do not have any more elements, we have null values. So then we will print the right subtree of 2. The right subtree of 2 will be having number 5, and then the left subtree of 1 will be finished. After this, what we have to do? We have to print the right subtree of 1, which will be starting with 3. Then we have to print the left subtree of 3, and then we will be printing the right subtree of 3. So in this way, what we are achieving is we are achieving the depth first search of the binary search tree, right? Binary tree. So here we have completed all this. So in the starting, how do we implement this? How do we do this depth first search using the stack? So first what we have to do, first we have to take the root node and place it in the stack, right? It will be our first element. And what will be our method? We will first place the current element, right? Then we will push out that current element. We will push out and print the element, right? We will push out and print the pop out and print the element. Then we will add the left side and the right side into the stack. Okay, so first we have added 1 into the stack. Now our next operation will be the popping out of 1 and adding 2 and 3 into the stack. So we have removed 1 now, and 1 is printed. What we have to achieve is 1, 2, then we have to print 4, then 5, then 3, then 6, then 7, right? So we have popped out 1 and we have added 3 and 2. Why we have added right 1 into the stack and left 1 after it? Because we have to print the left subtree first. So for printing the left subtree first, we have to keep it at the top of the stack. So for keeping it at the top, we have to first add right subtree into the stack, and then we have to add the left subtree into the stack. So what we have performed here is we have performed a pop operation, which will be printing 1 here, and then we have performed 2 push operations which will be adding the right element and the left element in the stack. So after adding 3 and 2, we will see that the next operation which we will be performing is हम 2 को बाहर निकाल देंगे, right? 5 will we take out 2 outside because हमको ये traversal चाहिए depth first search में. So लेफ्ट सब ट्री का हमारा जो करंट एलिमेंट है, हमने इसको पॉप आउट कर दिया, 2 को हमने पॉप आउट कर दिया यहाँ से, एंड हमने उसके नोड्स को डाल दिया, उसके लेफ्ट और राइट चाइल्ड को डाल दिया, जो कि है हमारा 4 and 5, राइट? सो हमने 2 को हमने निकाल दिया यहाँ से, एंड देन वी एडेड 4 and 5 इनटू द स्टैक, राइट? सो हमारा 1 भी प्रिंट हो गया है, हमारा 2 भी प्रिंट हो गया है. नाउ व्हाट वी हैव टू डू, वी हैव टू ऐड the childs of 4 and 5, बट क्योंकि उनके चाइल्ड नल है, इसलिए हमको ये चीज ध्यान रखनी है कि हमको नल वैल्यूज स्टैक के अंदर नहीं डालनी है. सो क्योंकि हम नल वैल्यूज यहाँ पे नहीं डालेंगे, सो हमको नेक्स्ट ऑपरेशन क्या होगा कि अगर हम नल वैल्यूज दोनों पुश नहीं करेंगे तो नेक्स्ट ऑपरेशन होगा टॉप एलिमेंट को पॉप आउट करना. सो करेंटली हमारा टॉप एलिमेंट क्या है, 4 है. सो हमने 4 को स्टैक में से रिमूव कर दिया, एंड हियर वी हैव एडेड 4. उसके कोई भी चाइल्ड नहीं थे, इसलिए हमने 4 को ऐड कर दिया, एंड हियर इज व्हाट यू सी कि हमारा फर्स्ट प्रिंट हो गया, हमारा सेकंड प्रिंट हो गया, एंड फोर्थ प्रिंट हो गया. 5 के प्रिंट होने के बाद हमारा पूरा ट्रेवर्सल ऑफ करंट नोड अगर हमारा 2 कंसिडर करेंगे तो हमारा ये पूरा करंट नोड ट्रेवर्स हो चुका होगा. क्योंकि अभी करंट एलिमेंट टॉप पे 5 है, तो हमको 5 को पॉप आउट करना होगा, राइट? एंड उसके नोड्स डालने होंगे, क्योंकि इसके ये भी एक लीफ नोड है एंड इसके पास भी कोई लेफ्ट सब ट्री नहीं है और राइट सब ट्री नहीं है, इसलिए हम इसके नोट्स भी हम स्टैक के अंदर नहीं डालने वाले, राइट? सो 5 को हमने प्रिंट करवा दिया. नाउ व्हाट वी हैव टू डू, वी हैव टू गो टू द राइट साइड ऑफ 1, बिकॉज 1 का पूरा लेफ्ट सब ट्री तो हमने पूरा कंप्लीट कर लिया है, राइट? 2, 4, 5 पूरा कंप्लीट हो चुका है. सो अब हमको 3, 6 एंड 7 को कंसिडर करना है. अब इसको कंसिडर कैसे करेंगे, क्योंकि टॉप एलिमेंट हमारा 3 है, तो हम सेम ऑपरेशन परफॉर्म करेंगे, 3 को ऐड कर दिया, उसके बाद क्या करा, उसके जो चाइल्ड एलिमेंट्स थे उनको भी ऐड कर दिया। सो फर्स्ट हमने 7 को ऐड करा क्योंकि वो राइट सब ट्री है, एंड देन हमने 6 को भी ऐड कर दिया स्टैक के अंदर। इसके बाद क्या ऑपरेशन परफॉर्म होंगे, 6 को भी पॉप कर देंगे हम और 7 को भी पॉप आउट कर देंगे। सो इस तरह से क्या होगा, वी विल बी हैविंग द डिजायर्ड रिजल्ट। क्या करा हमने, सबसे पहले करेंट नोड को प्रिंट करा, फिर उसके लेफ्ट सब ट्री को प्रिंट करा, फिर उसके जो लेफ्ट सब ट्री है उसके नीचे जो भी लेवल है उसमें भी हमने सेम तरीके मेथड इस्तेमाल करी। यहाँ पे भी लेफ्ट सब ट्री, देन राइट वन, एंड देन ये कंप्लीट हो जाने के बाद हमने 1 के राइट सब ट्री को कवर अप करा एंड उसके भी सारे एलिमेंट्स सेम ऑर्डर में हमने प्रिंट करवाने की कोशिश करी है। सो ये अचीव करने के लिए हम स्टैक का यूज कर सकते हैं, एंड ध्यान रखना है कि ये प्री ऑर्डर ट्रेवर्सल है। सो प्री ऑर्डर ट्रेवर्सल करने के लिए हम स्टैक का यूज करते हैं, एंड पोस्ट ऑर्डर एंड इन ऑर्डर ट्रेवर्सल भी हम स्टैक के थ्रू कर सकते हैं। आपको ये करके लाना है कि आपको देख के आना है कि इसको कैसे करते हैं, राइट। ये आपका होमवर्क है। सो अभी के सेशन में हमने DFS को देख लिया एक बार, राइट। सो सर मैं BFS भी कंटिन्यू करूँ या कुछ एक्सप्लेनेशन बाकी है?
Yes, sure.
ओके, सो DFS कंप्लीट होने के बाद लेट्स स्टार्ट विद BFS। यहाँ पे हमको देखना है कि हमारे रिक्वायरमेंट क्या है। फर्स्ट रिक्वायरमेंट है कि हमको लेवल 0 मतलब हमारा डेप्थ 0 होगा, उनके सारे एलिमेंट्स को प्रिंट करवाना है। देन लेवल 1 के सारे एलिमेंट्स को प्रिंट करवाना है। देन लेवल 2 के सारे एलिमेंट्स को प्रिंट करवाना है, जिनका ऑर्डर होगा 1 सबसे पहले प्रिंट होगा, फिर 2 एंड 3 प्रिंट होगा, एंड देन जो सेकेंड लेवल पे एलिमेंट्स होंगे 4, 5, 6 एंड 7 इनको प्रिंट करेंगे, राइट। सो इसके लिए हमारे पास ऑपरेशन क्या होगा, कुछ सिमिलर स्टैक के जैसे सिमिलर होगा, बट क्यू के अंदर प्रॉपर्टी क्या होती है कि यहाँ से एलिमेंट बाहर निकलेंगे एंड यहाँ से एलिमेंट अंदर आएंगे, राइट। सो जो हमारा अभी करंट एलिमेंट है वो है 1, तो 1 को हमने क्या करा, एन क्यू कर दिया। हमने क्यू के अंदर सबसे पहले 1 को डाला, राइट, क्योंकि हमको सबसे पहले यहाँ पे 1 चाहिए। सो हमने क्यू के जो टॉप मोस्ट एलिमेंट है उसको डी क्यू करवा दिया यहाँ से, राइट, एंड उसकी वैल्यू हमने यहाँ पे प्रिंट करवा दी। सो सबसे पहला ऑपरेशन हमारा यही होगा, हम सबसे पहले 1 को प्रिंट करवा देंगे, एंड देन हमको डालने पड़ेंगे उसके लेफ्ट सब ट्री एंड राइट सब ट्री को। लेफ्ट एंड राइट सब ट्री को हमको क्यू के अंदर डालना पड़ेगा, एंड इसकी मेथड क्या होगी कि सबसे पहले हमको 1 प्रिंट करवाना था, फिर 2 और 3 प्रिंट करवाना था, एंड क्यूज के अंदर आपको ये प्रॉपर्टी पता है कि फर्स्ट इन फर्स्ट आउट ऑपरेशन होता है। सो फर्स्ट इन फर्स्ट आउट में ये होता है कि जो सबसे पहले नोड आएगा वही सबसे पहले प्रिंट होगा और उसके बाद ही उसके चाइल्ड नोड्स प्रिंट होंगे। सो फर्स्ट इन फर्स्ट आउट में हम देखेंगे कि हमको क्योंकि 2 सबसे पहले प्रिंट करवाना है, उसके बाद 3 को प्रिंट करवाना है, इसलिए हम सबसे पहले 2 को क्यू के अंदर डालेंगे और 2 ही सबसे पहले क्यू के बाहर आएगा, राइट। सो अभी तक हमने क्या ऑपरेशन परफॉर्म कर लिए थे, करंट नोड को हमने क्यू के अंदर डाल दिया था, और करंट नोड को निकालने के बाद हमने उसका लेफ्ट चाइल्ड एंड राइट चाइल्ड दोनों को हमने क्यू के अंदर डाल दिया, राइट। इसके बाद की ऑपरेशन क्या होगी, सेम वही, जो हमारा सबसे टॉप पे एलिमेंट रहेगा उसको हमको क्यू से बाहर निकालना है, राइट। सो डी क्यू ऑपरेशन की मदद से हम 2 को निकालेंगे और उसके लेफ्ट और राइट चाइल्ड्स को क्यू के अंदर डालेंगे। सो जैसा कि हमको ऑर्डर चाहिए था 1, 2, 3, 4, 5, 6, 7, सो इसके मुताबिक हमने 1 और 2 को तो प्रिंट करवा लिया है। नेक्स्ट व्हाट वी हैव टू डू, यहाँ पे सेम ऑपरेशन परफॉर्म करना है। 2 को हमने जैसे निकालने के बाद 4 और 5 को डाला, सिमिलरली हम 3 को निकालने के बाद 3 को प्रिंट करवा देंगे एंड उसके लेफ्ट चाइल्ड और राइट चाइल्ड को प्रिंट करवा देंगे, राइट। सो हमने 3 को निकाला एंड उसके बाद उसके लेफ्ट और राइट चाइल्ड जो 6 और 7 है उसको यहाँ से एन क्यू कर दिया। सो आप देख रहे हो कि हमारे 2 लेवल्स प्रिंट हो चुके हैं, लेवल 0 एंड लेवल 1 हमारे प्रिंट हो चुके हैं, एंड सिमिलर ऑपरेशन हमको कंटिन्यू करना है। 4 हमारा अभी नेक्स्ट टॉप मोस्ट एलिमेंट है, 4 को हमको यहाँ से एन क्यू करना पड़ेगा और उसके लेफ्ट और राइट चाइल्ड को हमको पुश करना पड़ेगा, बट क्योंकि उसके लेफ्ट एंड राइट चाइल्ड है ही नहीं, वो नल वैल्यूज है, तो हम नल वैल्यूज तो क्यू के अंदर प्रिंट करते नहीं है, क्यू के अंदर ऐड नहीं करते हैं। सो अब क्या होगा, 4 बाहर आ जाएगा एंड 4 को हम प्रिंट करवा देंगे, राइट। और कुछ भी यहाँ से एनक्यू नहीं करने वाले, ठीक है। सो 4 भी यहाँ पे प्रिंट हो गया। नेक्स्ट व्हाट वी हैव इज 5 एंड देन वी हैव 6 एंड देन वी हैव 7। सो ये जो चारों एलिमेंट्स हैं, क्योंकि इनके कोई भी चाइल्ड्स नहीं है, लेफ्ट चाइल्ड नहीं है और राइट चाइल्ड नहीं है, इसलिए ये सारे एलिमेंट पॉप आउट हो जाएंगे, करेक्ट। और इसके कोई भी चाइल्ड्स होंगे नहीं, इसलिए हम कोई भी एन की ऑपरेशन परफॉर्म नहीं करेंगे। तो एट दी एंड हमको क्या मिल जाएगा कि लेवल 0 भी प्रिंट हो गया हमारा, फिर लेवल 1 भी प्रिंट हो गया एंड देन हमारा लेवल 2 भी प्रिंट हो गया इन द ऑर्डर विच वी वांटेड। सो ये क्या हो गया था हमारा बीएफएस ट्रैवर्सल। एंड इसका कंफर्मेशन कैसे मिलता है, स्टैक एंड क्यू दोनों में, जब हमारा स्टैक और क्यू दोनों एम्प्टी हो जाएंगे, सो दिस इज अ कंफर्मेशन कि जितने भी एलिमेंट्स ऐड हुए हैं स्टैक और क्यू में वो सारे एलिमेंट्स प्रिंट आउट हो चुके हैं। तभी जाके ये ऑर्डर, ये लेवल अचीव होगा कि ये पूरा स्टैक एंड क्यू इनिशियल लेवल पे वापस पहुंच जाएगा। सो फाइनल कंडीशन जो टर्मिनेट करने के लिए चाहिए होती है वो यह होती है कि आपका स्टैक और क्यू एम्प्टी हो जाए, सो आप वहां पर ही टर्मिनेट कर दो एंड आपका फाइनल आंसर आपको प्रिंट करवा देना है। सो दिस इज ऑल अबाउट traversal of tree through BFS and DFS with the help of stacks and queues.
Thanks
So
a lot.
Murtaza sir will continue from here.
Yeah, thanks a lot, Ivan. So yeah, let's continue with other things. So yeah, you have like seen the traversals, right? The pre-order you have seen, in order and post-order. You should definitely try it. Even in recursion, what happens is basically recursion has an inbuilt stack. So BFS mein we are always using the queue, that's no doubt. This is the pseudocode for BFS, which you have already seen, that create an empty queue, then there's a root, and in a loop print the node, and in queue its children. Ivan has already explained this, so I won't explain it again. And yeah, in this recursion, basically there is a inbuilt stack, so all of these values are stored in a stack if you use recursion, and if you do not use recursion, then you will have to create your own stack and use it. So this is how, even in tree, different like other data structures are used. Like you saw, like in order to traverse a tree, you will need a stack or a queue. So that's how you use data structures. Like that's how the trees, the stacks and the queues are actually used. Tree are also used for different things. We will get to it. So yeah, this question. So this is the level order traversal code if you need it in Java, but you can, as always, get it from Geek for Geeks. I have like reference it in the end of this presentation. A quick exercise for you guys. Could you please, like quickly, like I will only like we only have 2 minutes, like so, like write. I guess write the post order traversal. Could you please quickly write the post order traversal for this tree? Guys, are you like responding? You know what post order traversal, right? So like I will explain it first and then we will check the comments. So basically, just a quick explanation. First, we'll start with the root node. Then, because it's a post order, we always process the current node at the last. So we will go towards the end, like we will go to 5, then we will go to 9. It has no children, so we have to process it. So 9 will be the first one. Then we go to 5, and then we go to right subtree first, because again the current node is processed at the last. We move to 7, then we move to 1. So we have 1 here, then we move to 12 and then to 2. So 2, then there's 12, then there's 7, then there's 5, and so on. I hope you guys have an answer, and if you guys don't have, here is the answer. Right. So this these are the answers for this. You can practice it later. For about the height of the binary tree. So this is one of the main algorithms that we will be studying today. So let's quickly get into it, because we have time foundation. So I will be explaining it quickly. So first of all, what is the height? I said it before. It is the deepest, the path, length of the path from the deepest node in the subtree of the current node. So the for the algorithm, let's calculate the height of the entire tree. We are calculating the height of the binary tree. Height of the binary tree is the longest path between a root node and a leaf node. So I think you can already see the longest path. It's this to this. So this is the longest path between the root node and the leaf node. So let's calculate it quickly. So basically, how the algorithm goes is this is the function bt height, binary tree height, and if the root is null, then we return 0. So basically, if we are on these null nodes here, so because D is a leaf node and it will have null nodes, so we basically return 0 because it does not have anything. So when we return 0 here, the height of the D is basically 0. You already know this. So we will begin our recursion from node A, and you know what recursion is, function calling itself. So according to this algorithm, we will go to the left subtree first, then we will go to the right subtree, and then we will calculate the maximum of the left and the right heights. Right, and we will return +1. Why do we return +1? We will see in a moment. So we start from A, we go to the left subtree first, B, and then again we go to the left, that is D first. So in D, we see that we have encountered null nodes and they basically return 0 based on its null condition. So we have this 0 here, and we return we return maximum of both of these, that is 0 and 0, max is 0, and then we return max of both these +1. So we return 1 here, and the now the left subtree has returned the value 1 here. Why it has returned 1 here? Because there is a path between D and B. So the length of this path is 1. That's why basically from D, it will calculate the maximum height of D, and then because B is its parent, so obviously the height will be incremented once, because there's a path between B and D. There's a edge between B and D, to be precise. And the right subtree of D, it's null, so it will return 0 here. So max of 0 and 1 is 1, obviously, and this B will return max of 0 and 1 is 1 plus 1, that is, it will return 2 here. So currently 2 the left subtree has given a value 2 to this A. Similarly, we will traverse this A in this fashion. So let's write the heights here, 0, the height of this was 1, and the left subtree has returned 2 here. So we will traverse the right, and then we will go to the left, and then we will go to the left, and in similar fashion this will see that it has null nodes. So basically it will return 0, the height will be 0. Then there is a null node here, so it will be max of 0 and 1. So so it will be max of, exactly, it will be max of 0, it will return 1 here, and it will return 0 here. So it will be max of 0 and 1, the height will be 1, then it's again max of 2, that is 1 plus 1, and here the height of this is 0, so it will return 0 plus 1, that is 1 here. Then you know it, max of 2 and 1, that would be 2, and 2 plus 1 would be returned here, so 3 will be returned here. So at this A node we have the left is giving us 2 and right is giving us 3. So the height is the maximum of these two, that is 3. So you can see here, this is the height of the subtree, that is the length of the path between A, that is the root, and the deepest leaf, that is G. So it's 1, 2, and 3. So there are 3 edges, so height is 3. Depth of the node, you already know, they are the levels of a binary tree, and this is kind of a homework for you guys. I have not yet mentioned any code and stuff. You should try it on your own. It's basically finding the levels of every node. Like this, take this as a data structure and store the depth in every node. Like for example, the depth in both these nodes will be 4. The depth here will be 3, 2, 2, 2. So basically, like try this out for yourself. I've already mentioned the links, and you will easily get this question, and you can practice it on Geek for Geeks. This is the star of today, which is the diameter of the binary tree. So just let me check. Yeah. So I would like to play like you to say that you should pay close attention to this. We have just now solved the height of a binary tree, right? So guys, could you please write in the chat box, like what do you think is the diameter of the binary tree? What do you think this diameter thing is? Quickly, please. What is the diameter in a circle? Like for example, let's take a circle. So what should be the diameter inside the circle? It is basically the longest chord. So here, okay, max height of node in a tree. Yeah, so that's one thing for sure. The height of root node is always the maximum. Yeah, okay, I have gotten the answer. Current answer is that it's the longest path. So that's correct. In a circle, it is the longest chord or the longest distance between 2 points on a circle. In a tree, it is the longest possible path present inside a tree. So let's quickly get into it. So we can see here the longest possible path here is this path, and the length is 1, 2, 3, 4, 5, 6, 7, 8. So 8 is the length of the diameter of this tree, and yeah, this path is passing through the root node. But here you can see that this is the root node, but here the diameter is this. So yeah, it's not passing through the root node. So it's not a guarantee that diameter always passes through the root node. So let's get into how do you get this diameter. So there are mainly 3 cases for every recursive step in the diameter of a binary tree. Those 3 cases are either your diameter is present in the left subtree, or your diameter is maybe present in the right subtree, or maybe it passes through the current node or the root node. So diameter is present in the left subtree, diameter is present in the right subtree, and the longest path between the leaves that goes through the root. So a diameter can either be present on the left side or the right side, or it goes through the current root. So these are the 3 cases which we need to take care of to find the diameter of the binary tree. Algorithm of a recursive method, it's the same as the 3 cases. Find the diameter of the left subtree, find the diameter of the right subtree, and then you can you can basically calculate the height of the left subtree and the right subtree and basically merge those two. So for example, let's look here. Like at this point here, the height of this node was 2, and the height of this node was 1, 2, 3, and 4. So it was 4. So basically, you can merge these two heights and form the diameter. So it's 2 plus 4 is 6, and these two nodes here, so these two will also contribute, so plus 2, that is 8. So that is how it works. So basically you can first calculate the diameter of the left subtree and the right subtree and get the heights of those two subtrees and then merge them and compare it with the current diameter that is at the longest, and the greatest value among these three values would be the diameter of the binary tree. So it's actually quite simple, it's not that complicated. Like, you just need to like create a global variable which will store this diameter of the binary tree, and then you define the left height and the right height, and you get it from the recursive function, right? You create a utility function. It you can basically say it's a utility function called height, and it basically gives you the height of the left subtree and the right subtree. So what will be the diameter if like if we are talking about this subtree? So this is a leaf node, so it doesn't contain any children, so the diameter here is basically we return 0. That is the height of a null node is 0, and the height of a leaf node is also 0 basically. So what we get is we recursively move to the left and the right subtree. We move here first to the bottommost, then we calculate the diameter for this node, it's coming out to be 0. We calculate the diameter for this node, it's also coming out to be 0. Then we calculate the diameter of this node. So the node of this we get you already know from this height function that if like this, the height of this node is 0, it returns the max of the height of both of its children, that will be 0 because both the children are null, and it will return plus 1 here. So it gets 1 from left hand side and 0 from right hand side. So it's entirely similar thing. Both the heights like it's 0, it from both the sides it gets 1, right? So from both the sides it gets 1, and the height of this node is currently equal to 1. That is max of both of these. And then we can either have the diameter is either 0 or 0 here, or we can basically merge those two heights to form a new diameter, that is this. So we basically merge this 1 here or 1 from here, and combined they form 2. That is basically the diameter of this subtree. So we got diameter of this subtree. Similarly for this, we have 1 from left and we have 2 from right. So basically 2 plus 1, that is 3. So the diameter of this subtree will be equal to 3. And similarly, if we move inside this, so let me just quickly write the diameters of all of these. 0, 0. Then there's 1 because this is also a diameter for this subtree only. Then 2 for this because this is the diameter. Actually 3. It will be 1 plus 2. That will be 3. Then I will return the height here. Height will be the maximum of 1 and 2. That is the height of the left subtree and the right subtree. So I will quickly return max of these two. That will be 2 plus 1, that is 3 here. And then eventually the diameter will also be for this subtree. It will be 3. That is these 3 nodes. And then for this it will be 4. And then for this root node, it will combine to form the diameter, that is 4 plus I guess it was 3 here. Yeah, so it will combine to form basically 1 2. Okay, it was 2 here. 2 plus 1 will be 3, and 4 plus 1 will be 5. 3 plus 5 will be equal to 8. And we are maintaining a global variable, that is primarily because it is not guaranteed that the diameter always passes through the root node. For example, we have a global variable called diameter d is equals to some value called 0, for example. Then we like the diameter of this node will be 0, 0. We'll update this diameter with this function here, that is a dot answer is our diameter. So a dot answer is max of a dot answer. So we are comparing the existing value with the new value. What is the new value? The height of the left subtree and the height of the right subtree. So we are adding them and comparing it to the current value. So with every step, we are basically checking either the diameter has already been calculated in the previous step and that diameter is stored in a dot answer, or it will be calculated in the current step, that is the left height and the right height. So here the diameter, maximum diameter was already calculated on this node, but when we go to the root node, we get like 1 from here, and I guess 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5. Oh, okay, it's 5 actually. 3, 4, 5. Yeah. So we get 5 from here. So adding this 1 plus 5 will be equal to 6. But we know that we have already like calculated the diameter here, that is 1, 2, 3, 4, 5, 6, 7, 8. So the diameter was already present in this a dot answer, that is 8. But we are just like summing it up, the left height and the right height on the current node to get the diameter. So the answer will be the maximum of this, and the maximum of this will be stored in the diameter variable, that is our answer. Maximum of this will be 8, and so the diameter of the tree is 8. So at the end we will have the diameter of the tree in our answer global answer variable, which is a global variable. We are like defining static here simply because they are global, and if you are not a Java guy, then simply understand this as a global variable. If you know static, that's well and good. I've used these references, so please go to these, and if you have any doubts, connect with me on LinkedIn and follow Computer Club. And again, I have there's one more thing I would like to share with all of you. Like, I have prepared this document. So this document contains all the references as well as some lead code problems. So I would like recommend you guys to like go through these lead code problems. This is the diameter of the binary tree question, which is present here on the lead code. I was planning to solve it, but due to time constraints, we could not solve it. So if you want to like practice these, so I have like made a list of easy, medium, and hard questions. Please go through all of them and try it for yourself. And yeah, that's about it. All the best and thank you. And yeah, don't forget to give the quiz that is prepared by our friends at Creators Garage. So don't forget to give the quiz, and yeah, it's a really well-made quiz, so please give it. And yeah, that's it from my side. Murtaza Ali signing out.
I would like to thank our speaker, Mr. Murtaza Ali, on behalf of the team for taking his time off his busy schedule and enlightening us with knowledge. I would also like to thank all the attendees for being sincere listeners. All of you are requested to fill the feedback form and attempt the quiz in order to get your certificate. Thank you so much, sir.
Yeah, thanks a lot for having me.